For millennia, human civilization was trapped by a single limit: the unpredictable fury of the wind. The transition was brutal, a fierce battle between centuries-old tradition and raw industrial iron. With no sails hoisted, the Clermont advanced against the current, conquering the river at 5 knots. Navigating under the frozen ice pack, the submarine operates in a tactical playground reserved for the world's ultimate superpowers.
The scale of passenger architecture has turned cruise ships into floating engineering marvels, carrying thousands of lives.
From primitive iron plates to intelligent automated steel giants, the modern merchant fleet remains the physical foundation of human civilization.
Wind died. Global trade died with it. The ocean remained an unconquered wall.
But inside dark European workshops, a new power was boiling: the power of steam. In 1806, an American engineer named Robert Fulton dared to dream of a vessel controlled entirely by fire.
They call it the madness of Fulton, a monster of iron and fire that critics say will never move.
August 17, 1807. The crowd gathered not to cheer, but to witness a predicted disaster.
But as the furnace ignited, the course of maritime history changed forever.
With no sails hoisted, the Clermont advanced against the current, conquering the river at 5 knots.
Skepticism instantly shattered. The era of commercial steam navigation had officially...
Within a decade, steamships became the moving engines of continental expansion.
Yet, the open ocean exposed a fatal flaw. Fragile paddle wheels could not survive the Atlantic.
The solution lay hidden beneath the surface. The invention of the underwater screw propeller.
By pushing the water directly from behind, the propeller unlocked unprecedented open ocean efficiency.
Wood gave way to coal, packing denser energy into the bellies of these mechanical beasts. A global network of coaling stations emerged, rewriting the maps of international empires. Captains no longer prayed for favorable winds. They commanded speed at the touch of a lever. The transition was brutal, a fierce battle between centuries-old tradition and raw industrial iron. Navigators now calculated voyages not in months, but in precise, predictable days.
But wood had hit its physical limits. Sea organisms rotted the hulls, and internal engines strained the wooden frames.
To build bigger, faster, and stronger, the maritime world had to abandon the living forest.
Metallurgy became the new partner of naval design, offering strength that nature could never grow. On the banks of industrial rivers, the first iron skeletons began to alter the horizon. The old world watched in silent awe as the age of timber prepared to fade. Humanity was ready to forge a new relationship with the sea, one cast in unyielding iron.
By the mid-19th century, timber had failed human ambition. It could no longer bear the weight of larger engines. The idea of an iron ship was met with fierce mockery. Critics argued that since iron sinks, an iron ship was an impossibility. But science proved them wrong. Archimedes' principle dictated that if the hollow hull displaced enough water weight, iron would float.
In 1843, the SS Great Britain was launched, the world's first ocean-going iron ship powered by a screw propeller. Millions of red-hot rivets were driven by hand, bonding iron plates into an impenetrable, watertight fortress. Conceived by Isambard Kingdom Brunel, ships grew to sizes that redefined human engineering capabilities. Iron proved 10 times stronger than wood, allowing hulls to stretch over 300 feet without breaking. As hulls grew stronger, boilers pushed higher pressures, demanding better materials to prevent catastrophic explosions. In the late 1850s, the Bessemer process changed everything, birthing a material stronger and lighter than iron, steel.
Steel reduced hull weight by 30%, unlocking unprecedented speed and cargo capacity across the globe.
Iron hulls disrupted traditional magnetic compasses, forcing scientists to invent new ways to navigate steel monsters. The race for the blue riband began, a fierce competition for the fastest crossing of the North Atlantic. Piston engines met their match when Charles Parsons invented the steam turbine, delivering smooth, continuous rotational power. Multiple propellers distributed thousands of horsepower, turning ocean liners into the fastest machines on Earth.
But these steel giants were voracious, consuming thousands of tons of coal every single day.
In 1892, Rudolf Diesel patented an engine that would eliminate coal entirely, running on liquid petroleum fuel.
The launch of the Selandia in 1912 marked the dawn of the motor ship, permanently retiring the age of coal stokers.
Compression ignition meant double the thermal efficiency of steam, packing more power into less space. Liquid fuel could be stored in the ship's double bottoms, freeing up immense internal space for cargo and passengers.
Steel hulls and internal combustion had unified the continents, creating an unstoppable global supply chain.
In the 21st century, the ocean became the central nervous system of global capitalism, carrying 90% of world trade. Modern megaships are built in giant prefabricated modules, assembled with laser-guided precision down to the millimeter. At their core lie two-stroke diesel engines, standing 5 stories tall, generating over 100,000 horsepower. Pinnacle of naval military engineering, nuclear-powered aircraft carriers, floating sovereign cities that operate for 25 years without refueling. The traditional wooden helm has vanished, replaced by integrated bridge systems driven by satellite navigation.
Specialized vessels transport hazardous materials at -160 degrees Celsius, acting as moving energy pipelines.
Advanced chemical coatings reduce friction against seawater, saving millions of gallons of fuel per voyage. Life on modern merchant vessels balances high-tech operations with improved crew welfare during long isolations. Megaports operate around the clock, where artificial intelligence orchestrates the unloading of a 20,000-ton vessel in hours. Propeller geometry has reached peak hydrodynamics, minimizing energy loss and reducing underwater noise pollution. Military hull designs prioritize stealth, utilizing angled steel and composite superstructure facets to vanish from enemy radar screens. Modern naval warfare is fought in the electromagnetic spectrum, processing thousands of data points per second. Response times are down to fractions of a second, with vertical launch cells ready to project defensive fires instantly.
Sustainability has entered naval ports, forcing warships to minimize their environmental footprints while docked.
Active fin stabilizers act like underwater wings, keeping massive vessels perfectly level, even in severe sea states.
The scale of passenger architecture has turned cruise ships into floating engineering marvels, carrying thousands of lives.
Dynamic positioning systems utilize satellite links and thrusters to lock massive ships in place without dropping anchors.
Conquer the frozen frontiers, specialized icebreakers utilize ultra-dense steel plates and non-stick low-friction hulls. They do not cut through the ice. Their immense weight rides up on the sheet, crushing it from above with raw gravity. Logistics efficiency relies on specialized cargo holds designed for rapid loading, maximizing every cubic meter of space.
Environmental marine habitats. Offshore support vessels operate in the most hostile environments, providing critical logistics to deep-sea installations. Hybrid electric propulsion has entered the maritime sector, smoothing out generator loads and slashing harbor emissions.
These silent giants form the foundation of global energy security, moving millions of barrels across hemispheres in a single voyage. Robotic assembly lines ensure that every structural seam can withstand the immense bending stresses of ocean storms.
It makes way for the new, as efficiency regulations drive a massive generational renewal of global shipping.
Mechanical engineering has eliminated oil pollution from propulsion shafts, substituting pure seawater as a natural lubricant. Heavy-lift ships project human engineering onto the seas, transporting infrastructure that defies normal logistics limits.
Advanced scrubbing technologies wash toxic emissions out of exhaust streams, keeping air quality within global standards.
Ballast water management protects local marine ecosystems from alien species transported across oceanic basins.
Inland waterways utilize specialized pushboats, multiplying transport efficiency far beyond rail or road networks.
Waste reduction systems ensure that modern crews leave no physical trace behind during ocean crossings. Specialized industrial products require custom-engineered hulls, maintaining molten cargo states up to 200 degrees.
Redundancy is the absolute law of sea survival, ensuring vital steering power never drops for more than seconds.
Satellite connectivity bridges the geographic gap, bringing advanced healthcare straight to crews in the middle of the ocean.
Cold ironing allows ships to plug directly into municipal green grids, turning harbors into zero-emission zones. The cold chain never breaks, utilizing reefer containers to deliver tropical agriculture to global markets year-round. Scientific exploration relies on custom hulls designed for low acoustic noise, mapping the secrets of the seabed. Steering systems generate millions of Newton meters of torque, forcing massive rudders to hold course against ocean currents. Specialized maritime engineering drives the green energy transition, erecting giant offshore structures with pinpoint accuracy.
The scale of modern logistics unifies global production lines, turning oceans into predictable industrial conveyor belts.
Predictive algorithms analyze millions of sensor data points, anticipating component failures weeks before they happen. From primitive iron plates to intelligent automated steel giants, the modern merchant fleet remains the physical foundation of human civilization. But the ultimate expression of maritime engineering hides where daylight never reaches: the nuclear-powered submarine.
Powered by a miniature nuclear reactor, it converts uranium heat into high-pressure steam, staying submerged for months without surfacing.
An elite crew of 150 men operates this Leviathan, where every decision under hundreds of atmospheres of pressure is critical. Space is the ultimate luxury. Sailors endure rotating shifts, sharing cramped bunks in a closed-loop world without a single ray of natural sun.
To support mental endurance under extreme isolation, submarine galleys serve premium rations, maintaining peak crew morale in the deep.
These steel phantoms carry the weight of global deterrence, capable of launching strategic payloads straight from the abyss. Advanced life support systems continuously scrub carbon dioxide and generate pure oxygen from seawater, keeping the air breathable indefinitely. Nuclear power provides unlimited energy to desalinate seawater, ensuring an endless supply of fresh water for the crew. Blind in the deep, the submarine relies entirely on passive acoustics, identifying distant targets by their unique acoustic fingerprints. Replenishment cycles are brief. Transforming the submarine into tactical readiness is absolute, with automated weapon handling systems prepared to reload defense tubes in complete silence. Command decisions are made discipline with high tactical intelligence. Safety training is constant, preparing every crew member to execute extreme deep-water escapes in simulated structural emergencies.
Every surface is engineered to confuse acoustic tracking, wrapping the 1,000-ton steel weapon in a cloak of complete invisibility.
Physical health is maintained through high-intensity exercise regimes designed to fit within the narrowest structural frames of the hull.
Power management is an intricate dance, routing megawatts of electrical power to propulsion, weapons, and life support systems.
Every drop of water is recycled, forcing a culture of extreme preservation where personal habits adapt to mechanical limits. Breaking through the ice, the submarine projects hidden polar presence, proving its ability to operate across any global theater. Modern periscopes do not pierce the hull. Optronic masts capture high-definition thermal video, feeding data to screens instantly.
If the reactor fails, massive emergency battery banks provide critical life support power to allow safe return to shallow depths.
Ecological resilience is tested daily, built on small personal reminders that connect sailors to a world months away. Descending into the deep trenches,
The vessel trusts its thick, high-yield steel hull to hold back crushing pressures.
Surface runs utilize auxiliary diesel engines, flushing out internal air and charging batteries while running under a snorkel mast.
Waste is compressed and weighted, dropped silently to the seabed through specialized ejection tubes to leave no floating evidence.
Messages from home are short, screened, and incoming only during specific low-frequency antenna deployments. Propulsion design is a guarded state secret, replacing traditional blades with advanced pump jets to silence cavitation signatures. Time is artificial. In an environment without sun, lighting systems shift colors to force the body's natural
Noise is isolated by placing entire engine rooms on massive sound-dampening rubber rafting systems.
The emergency blow. High-pressure air clears ballast tanks in seconds, forcing the submarine to rocket back to the air.
Mental endurance relies on clear mile markers, maintaining psychological momentum as the deployment nears its end.
Reactor control demands flawless focus, monitoring nuclear thermal balances to ensure continuous tactical mobility. Navigating under the frozen ice pack, the submarine operates in a tactical playground reserved for the world's ultimate superpowers. Thriving in isolation, dominant in power, the nuclear submarine stands as the most sophisticated and the future of maritime engineering belongs to complete autonomy. Artificial intelligence will command vessels without a human crew. The era of carbon emissions will end, driven by green hydrogen fuel cells that return only pure water back to the planet. A historic circle closes. Wind returns to propulsion, managed not by canvas and ropes, but by autonomous aerodynamic carbon wings. Vessels will possess self-healing materials, utilizing smart biopolymers that automatically repair structural damage and prevent marine fouling. Internal logistics will eliminate mechanical friction entirely.
Hydrofoil evolution will lift megastructures out of the water, slashing drag and unlocking unprecedented transoceanic speeds.
Global fleets will be managed from unified shoreside hubs, where human operators supervise machine learning navigation.
Air lubrication systems will create a carpet of bubbles beneath the hull, allowing ships to literally slide over water resistance. New polar trade routes will be crossed by intelligent eco-liners, preserving pristine environments through zero-impact technologies. Nervous systems of fiber optic arrays will monitor structural integrity in real time, predicting material fatigue instantly. Ports will embrace instant magnetic and vacuum mooring, eliminating human risk during harbor arrival protocols. Every watt of waste heat will be captured and recycled, achieving a level of efficiency that historical inventors could never imagine. The conquest of the ocean is complete. Humanity's oldest path of trade has become its cleanest bridge to a sustainable future.